Okay, so we are back. We have been looking at this process of backward chaining or backward reasoning in logic, in particular in first order logic, and we found that there is this very interesting possibility of treating this backward chaining as a retrieval mechanism, where we are looking for answers essentially. That is there some entity which satisfies certain properties and so on. So, that is more like retrieval. It may also involve a bit of search essentially, trying to say okay, this is not the entity, this is not the entity and so on. So, that raises this very interesting possibilities, and we should try and get a feel of that now essentially. But let us start by looking at how backward chaining can be implemented essentially. So, remember that what is given to you is a knowledge base. So, for example, in this our standard knowledge base that we have, not standard in the sense our favorite knowledge base about Alice, it has these statements P and Q, P implies R, R and S implies T, not Q or S, and not U and not V. We want to see how backward chaining would operate. So, our goal is of course, this statement T. So, is T true or not? In forward chaining, we kept adding new facts till we struck upon T. In backward chaining, we are more focused. We start with T and ask what is it that will make T true? Is that there in the knowledge base or not? So, is T true? We answer this by backward chaining. First, we have transformed our program a little bit here. We have replaced not Q or S by saying Q implies S. It just makes life a little bit simpler, and we have broken down this formula not U and not V into two separate formulas essentially. The rest of the program is the same, and the way that we manage backward chaining is that we maintain a goal set, and what this goal set contains is the things that you want to show to be true essentially. Our termination criteria will be when that goal set becomes empty, which means you have shown whatever you wanted to show. So, let us see, we want to see whether goal is true. So, T is the given goal and we put it in this set and this thing. Then because we have a rule which says that rule number 4, which says that R and S implies T, we remove T from the goal set and add R and S instead. So, this question mark, not the question mark, the comma should be treated as an AND essentially, because it is a set, we are not writing AND, but treating it as a set of statements which we want to show to be true. So, we will of course handle them one by one. So, let us say we handle R. So, we remove R from the knowledge base from the goal set, and we find that there is a rule which says that rule number 3 in fact, which says that P implies R. So, we are saying instead of showing R, you can show P, and that is good enough. P is there in the knowledge base, the very first statement P is true. So, we do not have to do anything further there, no more chaining is required. That leaves us with S. Now, we can backward chain over statement number 5, which says Q implies S, and say that instead of showing S, show whether Q is true, and luckily for us Q has been given to us as a fact essentially. So, we are left with the empty goal set, and we can terminate at that point. So, this is how we operate here. We start with adding the goal to the goal set, we keep regressing to sub goals as we can call them, till we do not have any sub goals left to solve or to show essentially. Depending on from which perspective you are looking, you sometimes tend to use slightly different terminology. From the search perspective, from AND OR trees for example, you would say solve essentially, and which is what we will also see in a short while. So, if you have conjunctive antecedents, in first order logic, and you have a goal of the kind R question mark x, which means, remember, is there an x such that R of x will be true essentially, and the rule is that P of x and Q of x implies R of x. Then we start with the goal R of x, and then it means we have to replace it with two goals, P of x and Q of x essentially. We can think of this as an AND node if you want to visualize the search space, because eventually these programs are going to do search in some form. We can think of this as an AND node, and then AND OR graphs are standard graphs which we can study independently. To solve R, you must solve both P and Q, and therefore, you go from R to P and Q. And this line here, it says that this is an AND node, that it is not a choice, you have to do both of them. So, let us illustrate this with a small toy example, which is talking about toys, and we are talking, in particular, it is talking about something categorizing toys as nice toys. Some rules which we have got from somewhere, and we have two rules. One says that if x is green, the first rule says if x is green and if x is circular, then it is a nice toy. The second rule says if x is red and x is a square, then it is a nice toy. So, green and circle, red and square. What we know about various objects is that A is green. So, as you can see the facts as they call them, everything is in the knowledge base in practice. A is green, B is green, C is a circle, C is red, D is red, D is also a square, E is a circle. If we visualize this as a search tree, then it is an AND OR tree, and you can see that if you want to solve for the goal nice toy x, you can either apply rule 1, which is going this side, or you can apply this thing. So, this is an OR choice, either this or that. But if you have to apply rule 1, then you must show that x is green, and you must also show that x is a circle. So, that is why this is an AND node here essentially. And then of course, we have the facts that if you want to show that something is green, you can show that yes, A is green, or you can show that B is green. So, you can try both options, and that is again an OR choice. So, to show that there exists a nice toy in our knowledge base, we will have to search over this space somehow, and that is what backward chaining has to do essentially. It is a little bit different from forward chaining, because in forward chaining you did not care if you made some irrelevant deductions or irrelevant inferences, they would sit in the knowledge base somewhere, but you were not bothered about that, because the moment you saw your goal, you would say that I have succeeded essentially. But in backward chaining, you have to be more focused, in the sense that you want to show that something is true, and it is not that you can keep growing your set of goals. In fact, what we have seen in the process is that you replace a goal with sub goals, replace the sub goals with sub goals, and so on. But what we will see now is that if that process does not work, you will need to backtrack and try something else essentially. So, backward chaining has an element of search in it, it will have an element of backtracking in it. Forward chaining does not have that. You just keep growing the knowledge base, and it keeps growing and growing. At some point, the goal appears and you are happy. But it is not so easy to handle existential goals in forward chaining. It could be possible, because we have the rule of generalization, which says that if, for example, Q of A is true, then it is true that there exists an x q of x. So, you could use that, but at every step you have to do that extra step of generalization, which also could be subsumed by matching at some point. So, this is our search tree. Our goal is that is there a nice toy in the knowledge base, which we apply rule 1 and say that we have two sub goals now, that x must be green and x must be a circle if x is to be a nice toy, but the nice toy has been removed from the goal set. Then we look for x must be green. We find that yes, A is green, as you can see in the knowledge base here. We can throw it away, and now we have to show that A is a circle, but when we look at our collection of circles, we find that we do not have A in that. So, that will fail essentially. So, x equal to A, but the next goal will fail. So, because this was an AND node, that you have to show that something is green and something is the same thing is a circle, it does not work for A essentially. So, the algorithm will backtrack and say okay, maybe B, we can try B because you know that B is green. Then again we go and look for whether B is a circle or not, and again it fails. So, you can see the pattern of search that is here. You went down one branch, then you came back and tried something else and so on. So, there is a flavor of depth first search here. So, all that fails and we say that okay, we can't find a toy which is green and which is a circle. So, let us try the second rule. The second rule says that look for something that is red and which is a square essentially. So, the same kind of process happens. We go down looking for something which is red, and the first thing we find is that C is red. So, we say yes, C is red, but now we must show that C is a square, but C is not a square because there is only one square thing in our this thing. So, we have to backtrack from there, and then we say okay, let us see D is red. So, is D a square? And in this small nice example that I have constructed, D is indeed a square. So, search has succeeded, a goal set has become empty. We have found a value for x which is x equal to D, and we can say yes to this, and we can say x equal to D, that D is the toy that you are looking for. So, you can see that retrieval has been done through logical deduction, and it is the power of logic that you can do this thing. In fact, the whole idea of logic programming is that you can whatever you can do in programming, you can do with logic, and we will look at that a little bit later, not now, that how even arithmetic can be done using logic essentially. So, logic programming is a powerful idea. It says that logical reasoning, which means logical deduction, can be used for doing any kind of computation essentially. And it also focuses on the fact that we are doing goal based reasoning. So, there is some semblance of efficiency there essentially. We will revisit this question of backward chaining again later when we talk about efficiency. So, the solution, if you are thinking of this as search, is a subtree which is highlighted in the slightly thicker arrows here, that yes, what you are looking for, that nice toy, you follow this rule 2 and you can show that something is red, and you can show that D is red, and you can show that D is a square. So, you have found your toy, but you have in the process you have also shown that the statement that there exists a nice toy is true, and doing is just one side of the other side of the same coin. So, here is a preview of a actual Prolog program. We will look at Prolog a little bit later in this course. And the way to read Prolog programs is, again we will see this in more detail later, is that rules are written in a slightly different fashion in Prolog. So, let me state the problem here. The problem is that you are making an outing plan. Maybe you have got a new job or something, or maybe you have got very good grades in the courses that you are doing, and it is time to celebrate, and you are making an outing plan, and the outing plan is that you do something in the evening, then you watch a movie, and then you go for dinner essentially. So, that is expressed in the first line, which is should be seen as a logical statement, but we can defer that to later. Let us look at the fourth line, which is one component of the outing plan, which is dinner. And what this line says is, what the logic sentence written here says, is that if X is a restaurant and your friend who is coming with you for the celebration likes X, then that X will fit the dinner plan essentially. So, the rule of course is, if then it is a dinner plan. In Prolog, because it is goal directed, because it is backward chaining, because you are searching from goal to facts, we write the goal first and we write the facts after that, because matching can be done as you go down the file essentially. So, you write dinner plan first, and this sign can be read as if. X is a dinner plan if X is a restaurant and your friend likes X. In Prolog, uppercase is a variable. This is a Prolog convention. In our logic discussion, we said you can mark the mark a variable by a question mark. Prolog has its own ideas, and they say if you have variables, they must be in uppercase. If you have constants, they must be in lowercase. So, for example, since we are talking about restaurants, if you want to talk about Saravana Bhavan, which is a restaurant chain in Chennai, it started with Chennai and it is now there all over the world. It begins with lowercase. So, this is just Prolog convention. Constants are begin with lowercase, variables begin with uppercase essentially. So, we have these rules essentially. An outing plan XYZ is true, if you want to think of it like that. If there is an evening plan which is true, a movie plan which is true, and a dinner plan which is true, and for each of the three we have rules. In an evening plan is an outing X if X is an outing and your friend likes X. What are outings? Outing, we have said you can go to the mall, which is the most common thing nowadays. You can go to the beach if you happen to be in Chennai, or maybe you can go for a walk if you happen to be in the mountains, which is not mentioned here. And we have given you choices of 4 movies: The Matrix, Artificial Intelligence, Bhuvan Shom, 7 Samurai, and 2 restaurants. And we have also given you some data about what your friend likes, I think. So, this logic program will search through these things. So, I keep repeating that backward chaining involves search. It will search through these things till it finds values for x, y and z, which are the 3 variables here. And then of course, not only will it say that yes, you have a nice outing plan, it will say the outing plan is this and this and this essentially. And as we just discussed, backward chaining or Prolog will construct an AND OR tree, which is also called a goal tree, which is the same piece of data that I gave you in the form of a Prolog program, is shown here as a tree essentially. So, the stuff in the red is the facts that you know, that for example, Bhuvan Shom is a movie, that your friend likes going to the beach, and all these facts which are there in red, this thing, and the other things are parts of rules essentially. And the backward chaining will do this thing that we have started, that we will first put the goal as in the goal set, and initially the substitution is empty, and then you will break down the goal into those 3 components, and then you will try out the components one by one essentially. So, the evening plan,
first you look for an evening plan. It will say that you are looking for an outing such that your friend likes the outing, and then after that the other 2 goals which were there, which will also continue to remain there. So, evening plan has been removed and replaced by outing plan and likes friend that plan essentially. And then it will try through various things. As you can see, it will try the mall, and then it will try. It will find that every option that you tried with the mall did not work. Then you would backtrack and try the beach, and then a little bit of trial and error will happen, and eventually you will come up with a plan. At which point you will find that you have the empty goal set and you have the solution: x equal to beach, y is equal to the movie, the matrix, and z is dinner at Saravana Bhavan. So, not only have you shown that this statement that is there an outing plan, or is there exists an xyz such that outing plan xyz is true. So, logic programming and Prolog in particular will come back and say yes, x is the beach, y is the matrix, and z is Saravana Bhavan. So, this is showing the power of logical reasoning and showing that logic can be used for computation in general, for programming in particular. So, this is the search tree that we saw, and the 3 nodes highlighted here are the solution that it will find. It would have done this trial and error. It would have tried out mall, and it would have tried for mall, it would have tried every other combination and seeing whether it's working or not. We will come back to Prolog later in the course, after we are done with the basic part of logic essentially. Now, I want to end with this problem that we have seen earlier. This very small knowledge base, which was a propositional knowledge base, but our query will be first order query. The knowledge base was, if you remember, 4 statements, and where O was the binary predicate, M was the unary predicate, ABC were constant symbols, and we first asked when we described this knowledge base as to what is this talking about, and we saw that any set of sentences can be interpreted in more ways than one, and we already saw this essentially, that the meaning of what this binary predicate means, what this unary predicate means, what are the constants talking about, is externally supplied. It's in the mind of the beholder or the user. This thing, and we had seen 2 examples there. One was the blocks world example, and we had said that the 4 statements translate to these facts, that A is on B and B is on C, and A is not maroon, which is the statement here, and B is maroon. Of course, we did not know what this was, so I added that as a question mark. It's missing from the knowledge base. So we don't know whether B is maroon or whether C is maroon essentially. And we saw another one interpretation in which the domain was people and O stood for looking at, M stood for married, and ABC were three people. And we said that Betty is looking at Cuthbert. So the four statements are: Betty is looking at Cuthbert, Archie is looking at Betty, Cuthbert is married, Archie is not married. But we do not know about the marital status of Betty. Now, given this knowledge base, without going into the semantics, whether we are talking about the blocks world or whether we are talking about human people looking at each other, we want to ask this query. In first order logic, with the quantifiers, we are saying, does there exist an x and there's n a y such that oxy is true, not of mx is true, and my is true? In implicit quantifier form, you will not have this thing, but because it is an existential query, they would come with a question mark. Remember that in queries, a question mark denotes an existential variable. Does there exist an x? Does there exist a y? Of course, for us, it is often difficult to think in such abstract worlds. If you look at the two examples that we saw, then the interpretations of this query, this is a first order logic query, because it has a variable, it has variables and it has quantifiers. So in the blocks world, that query would mean, is there a non-maroon block on a maroon block? Now, if you remember, we had three blocks, A, B, and C. A was not maroon. B, we did not know whether it was maroon or not maroon. And C, which was at the bottom, was maroon. The question we are asking, is there a non-maroon block on a maroon block? In the world of people, we asked the question, which I had asked you earlier also, that is a not married person, if you want to say unmarried, but just to be logical, unmarried is same as not married. If a not married person is a not married person looking at a married one, that's a question that I would like you to think about. What I would like you to do is to pause the video at this point and think about this question for a few minutes, maybe 5 minutes, or as long as you feel like it, and come back with the answer. Is the query, or is this statement, if you want to say, which is a logical statement, exists x, y and oxy and not mx, my? Is this statement entailed by the knowledge base? The knowledge base is given to you, which is a propositional knowledge base. The query is a first order query. It is an existential query, that is there an x and y which satisfy this property? Is it entailed in the first place? And secondly, if it is entailed, is there a proof for that? So I want you to take a break here. Pause the video, think about this, and then come back to the same video. Okay, so I hope you have given some thought to this. The answer to that query is yes. I should write it here. Yes, it is clearly entailed. So, though it may not be clear on the initial time, it's true that this statement is true. It is entailed, essentially. That in the world of people, that yes, an unmarried person is looking at a married person. In the blocks world position, a non-maroon block is sitting on a maroon block. You should think about this and see why this is entailed. But given this knowledge base and given this query that we have, which is an existential query, neither forward chaining nor backward chaining is able to generate a proof. You should try this also. Just try out some methods and see, rewriting some things in forms of implication or something, and then do what chaining, and you will find that one cannot construct a proof for this query. Which means what? Which means that both forward chaining and backward chaining are incomplete. In first order logic, they are incomplete. The query is a first order query, remember that. And so what we will do next is to look at a method which is complete in first order logic. This method is called the resolution refutation system. It's a very recent method. It was discovered, I think, in 1965 or something by Robinson. And we will look at that next and spend some time studying that. Till then, ponder over this fact that here is some simple query whose answer hopefully is clear to you after some time. But there is no proof that this statement is true. So we will go to a complete method, which is the resolution refutation method, which I had mentioned some time ago. Is another method of proof by contradiction, but it's complete, which means that anything that is entailed can be shown by this method, which is obviously a very useful thing to have, I think. So till we come back to that, it's bye for now.